Hello everyone and welcome to this live webinar. I'm Sheldon Varco, the Membership Manager in New South Wales and South Australia here at AusMine, and I'm joined today by Ken Plozza, Head of Global Digitisation at Mining at BASF, to explore their Intelligent Mine offering where artificial intelligence meets chemistry. In his presentation today, Ken will provide insights into their digital journey, starting with the cassette tapes that they're famous for, through to the creation of the Intelligent Mine and its successful implementation across multiple sites globally. Applications for specific purposes, such as grinding, flotation, thickening, heap leach, stockpile, and pipeline pumping will also be showcased during this presentation. Following the presentation from Ken, there will be an opportunity for audience Q&A. You can use the Q&A button at the bottom of your screen to send your questions over at any time during the webinar. And you can also upvote on other questions that you most want answered by Ken. So without further ado, I'll now hand over to Ken to kick things off for us. Welcome.
Thanks, Sheldon. Yes, Ken Plozza here. Just one other...
Just on mute at the moment, Ken.
I need to unmute myself, do I? Can you hear me now?
Perfect.
Thank you, Sheldon. Thanks for the introduction. One other question that we probably want to make sure that we gets answered out of the webinar today is that big question that maybe some of you are asking is why a global chemical giant like BASF is actually involved in digital. So hopefully we'll get through to the end and you'll understand that. I reiterate to what Sheldon said, if you've got any questions, use that chat QA function to ask and we'll get to them towards the end. So with that in mind, let's get going. Now, it might have been some time since many of you whipped out the old BASF cassette tape to listen to some of your favourite tunes, but I think the story of our BASF cassette tape actually remains a really relevant example of how BASF's dedication to innovation, our ability to find the right partner, and how we stayed ahead of the technology curve. Did you know that we were one of the original players in the cassette business? Back in 1932, it actually begins. So we partnered with a German company called AEG, and we did a heap of research to develop the cassette tapes based upon that first magnetic sound recording device. We also invented the first hard copy coded tapes in 1950, the first long play tapes, I think it was around 53, and the first chrome tapes in 71. With the advent of the personal cassette tape and then later the VHS, BASF was the go-to brand for pretty much most of your music and movie collection. As a result of this continuous innovation, BASF actually became a household name and practically all over the world. And we keep getting asked even today, oh, you're BASF, you're the tape guys. But that journey didn't actually end with tapes. One thing that actually happened was that as we started to move forward, we recognized there was need to move further beyond tapes. And so once again, BASF invested and partnered with another company to produce ultraviolet sensitive dyes suitable for the emerging CD and DVD markets. Then, as that market matured, BASF invested further in research and development to find novel chemical solutions to aid the manufacturing of hard memory devices like your USB. So BASF have replicated this approach across many different industries and products over the years. And if you take a look around the room you're in right now, there's probably not many items that you can see that have not had some point or touch point of BASF solutions in their life cycle. Let's fast forward a little bit to 2017. So this is when our BASF mining team, we really recognized that need for our business to embrace the full potential of Industry 4.0. So what we wanted to do is we wanted to digitalize our mining expertise so that we could provide our excellent post-sales service to customers 24/7. So as a result, once again, BASF sought the right partner, and this time we found it in IntelliSense.io. IntelliSense, like BASF, now they're staffed by experts who understand mining and mineral processing. The products that they were developing at the time solved industry problems based on extensive experience dealing with those actual problems firsthand. So we partnered with them and we created the BASF Intelligent Mine powered by IntelliSense. Now, this solution combines chemical and process knowledge with software, data analytics, and AI expertise. And the result is a product that's built by mining experts to solve real mining problems. So let's have a bit of a deep look into, or a deeper look at least, not a deeper look into the Intelligent Mine. So our technology really begins with mining and processing first principles right at its core. This is a little bit different to the rest of the industry. So IntelliSense has spent 5 years, and our partnership a further 2 years, building physics-based and machine learning assets and models for mining-specific processes, all based around first principles. So our optimization as a service applications, they're ready to go solutions, and each robust application optimizes a specific process within the pit to port value chain. We also have financial and operation value drivers, and these are configured on-site dynamically, and the applications cooperate together to predict, simulate, and optimize the process. This provides high-value, real-time recommendations through your existing control systems, and I'm going to go through that in a moment as well. The software applications themselves, they come with data inputs, outputs, and cause and effect relationships already pre-baked into the model. So this pre-built model-driven product architecture ensures that when you do the site implementation, we focus on calibrating your models to your data parameters. This allows us to deliver outputs within the first 4 weeks of any implementation. And the journey then is about training your model on your data, rather than developing models from square one and building them up from scratch. Our first principles approach means that we can be quite agnostic about equipment, OEM, ore types. Additionally, we can work within your existing data architecture. And again, I'll talk a little bit about that in a moment. The platform and the applications also have inbuilt and configurable environmental, financial, and operational real-time virtual sensors, and these are there to drive value. These drivers provide the operator, the process, and their management insights into the potential lost opportunity of poor optimization. I think you can agree, having transparency over the cost of decisions that your team are making on a daily basis just helps to drive better outcomes. So you can see along the bottom of the chart there, these are our available applications. What we need to understand is these are all fed and linked by an underlying material model. Now this model transports the properties and the influence of that ore from the pit right the way through to the port, all in real time. We track and adjust our models based on physical and chemical properties of the process stream and the influence they have on the plant performance. So as an example, let's think of, say, ore hardness. Then this will impact your grinding rate, it's going to impact your wear inside your mill, the resulting P80, which then influences your flotation, your thickening processes. Our models, our grinding, our flotation, our thickener applications, they all use this information to help provide real-time optimization advice for these individual places. Let's now look at your actual process and see where you fit. So first, of course, we bring with the mine and the plant. Within that, we're expecting to see a whole series of processes that we have applications to support. Each one of these processes are going to have a series of sensors, a series of instrumentation, and your native control system. And all this is sitting on your OT network. What we then have is, in addition to those things, you have all these other data sets. So you might have, just looking at a few of those here, your block model, maybe some manual data, your ERP system, your maintenance system, even your own data lakes. And all of these systems, they all feed directly into our Brains app. And what we can then start to do is we can do some high quality data analysis and data cleanup to ensure that the quality of the data that's coming in is spot on and ready for use. We then build our material model and this transport model to basically start to understand how all this data connects. And from that point, you can then start to do some advanced analytics based on this information. And more importantly, start to get some real-time predictions coming out of that info and even real-time simulations. The ultimate aim of our products, though, is to provide, in addition to all these things, some real-time recommendations and real-time virtual sensors. So that information then is fed back to your operational team. Now we can feed it back through either an open loop, so i.e. straight through to your operator via either a web interface or directly through faceplates so that you can have it in your DCS system, or we can actually close the loop as well and actually write directly back to your underlying control system. So maybe just a different way to summarize all of that is what we're trying to do is we're trying to help your site make better decisions. So if we begin with helping a team to describe what's currently happening by looking at new insights from your data using the data lake, we can then start to actually look at diagnostic things about why things are actually happening using Brains app. the next thing we can then do is start allowing our prediction and simulation models to support your operations to make better decisions in real time. So you notice here that the actual decision, or the human input, I should say, is getting less and less. The final thing we want to do, of course, is to give you this optimized result and actually feed that through. So reduce the amount of human input to make really good decisions, and maybe even close the loop completely, and actually then make direct action in your underlying control system. So that's the general story about what the product is and how we've come together. Let's have a bit of a look at the actual portfolio itself. So BrainsApp we've spoken about before, that's our underlying platform. Next we have our Brains VOS. So VOS stands for Virtual Operations Simulator. And all this is, it's just an historian of all our predictions. And with that, what we can do is we can run non-intrusive simulations to really help understand opportunity lost. And what we do is we monitor the accuracy of the predictions by comparing them against the actual test results. And that's a really good way of then understanding how well the models are working. BrainsApp Lite is the next one there. So this is the on-premise version of BrainsApp. So I think we said before that we normally deploy in the cloud. Well, on some cases we need to deploy in the actual network directly on your site, and that just delivers a robust, low latency system that allows when you need to write directly to your control system, so there's no interruption. Of course, like any piece of software, we've got an academy. This academy is designed to give your team a certification, I can't say that word, ensuring that your staff are competent in use of our product. What else do we have? We spoke about the material model, just remembering that it real time tries to track and predict the properties of the material as it moves through your plant and the influence those properties have on your process. We have a reconciliation component within the underlying platform. This takes all your operation and performance data and helps to reconcile it into a single dynamic, single source of truth. And this decreases your uncertainty and your granular reporting. Many virtual sensors. So we spoke a little bit about virtual sensors, and I'll talk about those a little bit more when we get into the individual products. But the idea here is that you want to deliver more information about your process in real time. So in some cases, we can use virtual sensors to avoid the need for instrumentation because we can create filling gaps, or we can create really interesting relationships in our data lake that might combine live data with maybe product data. And that produces a really interesting set of information and helps you make better decisions in real time. Those value models, so this is a special class of virtual sensor. And the idea being here is that we try and accurately calculate and predict your asset operating costs, so in real time. It's looking at trying to find the lost opportunity or the value generated as you move through using our products. Quick look at the actual applications. This is just 5 of the ones that I've chosen. I'm going to go into a bit of a deep dive into grinding, thickening, and flotation. But we have stockpile. Now, what stockpile's trying to do is to allow for real-time spatial modeling of your stockpiling process. So we're taking information from your block model, all your truck movements, and then giving a really high level of spatial, both in time and area, about what's actually in your stockpile. That actually allows you then to manage and feed that information into your plant as it's coming through. We have our grinding application. This one here guides your METs and your operators to optimize for throughput and stability and overall equipment effectiveness. Our flotation app, this supports operation of the float circuit by looking at trying to increase mass pull and improve recovery. We've got a number of really interesting virtual sensors that look at things like gas holdup and bubble size, and we provide guidance on optimal airflows and chemical usage. The Thickener app, now this recommends a whole heap of set points to your operator and control system by doing real-time prediction, simulation, and optimization to ensure your thickener runs really robust and stable. It optimizes your underflow density to either maximum or whatever number you're targeting, maximizing your clear water and optimizes your chemical use. And the last one there is heap leach. So heap leach is sort of reverse of a stockpile, but the idea being here is that we can give you a lot of insight into how to operate your leach circuit on that heap and how to actually optimize your metal recovery. Let's have a look at grinding and some of the problems that we think the industry has and some of the solutions that we've looked at. So the first problem that we're going to look at today is liner wear. So we know the performance of a grinding mill depends heavily on the condition of the mill liners. And the problem is that most operations don't actually know what the state their liners are in unless they physically stop and inspect it. Now that's a costly and potentially hazardous exercise. The second challenge is ball charge. So knowing the ball charge level is critical for good mill operations. Having the wrong ball charge can have significant impact on your grinding efficiency, and stopping the mill to inspect the number of balls inside, that's going to impact on throughput. So our solution here is we create a series of virtual sensors that estimate both liner state or wear state and mill volume. So the liner state is critical for understanding the mill efficiency and particle trajectory. The mill volume is important in estimating actually the charge, how much is balls, how much is material. What we then have is a series of sensors that predict when the liner needs to be replaced. You can see here it's predicting the number of hours into the future that you'll need to replace your liners. And this therefore improves the performance of your mill because you're stopping less often on unplanned liner replacement and maintenance events, and thus it increases your overall throughput through the mill. For ball charge, our solution here is a number of virtual sensors that allow the operator to see in real time both the current ball charge and then prompts them when additional balls might be needed to maintain the right level. So you can see there, this items is telling the team they need to place some more balls in. This stabilizes the grinding performance. It avoids unnecessarily ball or mill liner costs and prevents unnecessary stoppages, thus increasing your throughput. If we go to a bit of a deeper look at this, so I spoke about a couple of virtual sensors. So everything starts in our models by looking at the inputs that are available. So if we have these inputs from a grinding point of view, we can then start looking at a number of models that we've created. These are the ones that we've got. From those models, we can then start to create virtual sensors. If we can then combine the output of those virtual sensors with the underlying feed material properties, we can then start doing some prediction. And what we're trying to do in this case is we're trying to make predictions around these items here: mill weight, power, overload probability, number ones here. Once you now can predict what's going to happen, the idea then is to put them through the optimizer. And from the optimizer's point of view, we now want to then give advice to your operational team about different control set points and how to actually run your overall grinding circuit in the most efficient way possible. So that's grinding. Let's take a look now at thickening. So one of the most critical issues that many thickeners face really is probably the variability of ore and the properties that it has on stable performance. Unexpected events occur, and when they do happen, each team member reacts differently, be it an individual or across a shift. And if in doubt, they tend to run the thickener at a less optimal level just to stay safe. The second significant issue caused by these changes in ore properties or process changes is clearly it's the reduction in optimal density, clarity, rake torque events, flock usage. So our solution is, I've tried to put a single chart up here to show you what's going on, and it's way more complicated than this, but it's tried to combine the material model, so we know what's coming, with other upstream applications if we have them, and put them all into our prediction, and so that we can actually predict what's happening to the thickener 1 full hour into the future. Now, based upon that 1 full hour of optimization, we can then apply that to our optimization models and then give real-time live optimization targets for things like underflow pump speed, flocculant dose, just to name a couple, to make proactive changes to the system now for what's basically going to be coming in the future. Now, this results in a stable thickener performance, even doing changes to your ore or operational changes. Additionally, I think it allows the operator, he can now focus on the source of the disruption rather than trying to fix the downstream impact of that disruption. Our solution also allows the operations to set rewards and goals that our actual models target in real time. So this is trying to make it as transparent as possible. So as conditions or key drivers change, the team can then adjust the models to target different KPIs. So the example that we've got here, what we've got is we're targeting bed pressure in this case. So we've set the rewards and the goal to target the lower limit and avoid the upper limit. So you can see then in that 48-hour periods before and after our recommendation in the middle there, it's characterized by that standard control loop wave that you see normally. with the operator or the control loop, whichever one's reacting, basically just reacting to the current conditions. But when we switch it over to the IntelliSense recommendation mode, our optimization model makes predictions and reacts to that future state 1 hour in advance. And the results are stable bed pressure, it tracks that lower limit and avoids that upper limit. Also, you can see in the example, our recommendations have also pushed the underflow density. So it's made it higher, but it's also tightened the deviation. So this results in a more stable thickener operation at a defined limit. Let's have a quick look now at the underlying part of the thickener app. So again, we've got those input feeds. We've got a number of virtual sensors and models. They get combined again into these into the prediction. We try and predict these items. From those predictions, we feed that into the optimizer, and then the optimizer gives you control set points around these items. Take a quick look at flotation. So in flotation, I think operators are often unsure of whether they're using the right amount of air and reagent in the flotation cell. And additionally, they don't often know how each of their flotation cells or the individual columns are performing and how they're contributing to the overall recoveries. So our solution is to provide a number of virtual sensors to give insight into that real-time recoveries. So this is an example of multiple roughers, and the red line is what the target recovery is. You've got 2 sets that aren't hitting it and 1 set that is. We'll also look at real-time bubble size. We look at real-time bubble flux area. And when you combine all that together, what we can then start to do is to give recommendations about the airflow required to maximize or optimize all 3 of these parameters. So once again, if we look at how our apps are built, so we have a number of inputs, we have our models, our virtual sensors that those models then attempt to create. We combine that together to start making predictions. We predict these items. We then feed that into our optimizer, and the optimizer then gives you feedback in terms of control set points for these clear items. So look, in closing, we think our unique approach delivers continuous value. The traditional approach to digitalization, we think it's a high risk approach where providers look to create custom builds for each site. So that's going to need high upfront costs to create and focus on adding more instruments, maybe to get more data. This approach takes longer to implement, needs maintenance, usually by you, the client, to ensure the models are adapted for new operating conditions. What our solution tries to look to do is it takes advantage of implementing pre-built models, as I said, based on this first principles approach, with processes and chemistry knowledge built into their core, reducing that upfront cost significantly. We make use of your existing instrumentation and create new data via virtual sensors, eliminating the need to spend capital so that you're digitally ready. The result of this is a rapid implementation journey. It probably takes between 3 to 4 months per application, and this provides fast value realization. Of course, now our offer is an optimization as a service. So what this means is that we're your ongoing partner beyond the implementation. We update the models, we upgrade the applications with new features and functions every 3 months, actually, in fact, 4 times a year. Plus changes to your process flow are incorporated directly into those updates. So what we think is, our goal here is to deliver success, not just software, and it's by combining all of these strengths, I think, that we actually are allowed to or able to achieve that. Sheldon, I'll throw it back to you because that's the end of the, I'll stop sharing and we can start the Q&A.
Fantastic. Thanks a lot for that, Ken, and certainly interesting to see the approach BASF have taken there to digitising your offering. And a very interesting journey you've been on. It's quite a breadth and scale of applications there that you now cover, and quite unique and impressive the way you're utilising and generating that information to drive operational transformation. So thanks a lot for that. As Ken mentioned, we do now have some time for audience Q&A. You can use the Q&A button at the bottom of your screen to submit any questions. We do also have a few questions there, and you can also upvote on those questions that you most want answered. So just to kick off with a question here from Marianne Ken. So how open are the models? Can teams open them and inspect why a prediction was made?
So all of our platform comes with APIs that we can allow staff from your team to begin to work with the models, right? To understand why the decision came about. They can take those models, we can allow the team to build on them. However, before any model then or change or is implemented on your site, it needs to go through some sort of quality or certification process to make sure that it's actually going to work on the Brains app. We would prefer to train your staff in understanding the models and retain them, and then use that platform to build new stuff around that topic. One thing, of course, we need to understand is that most of the models that are in the system are our IP, but we're there to try and support their development, to expand upon them and make them work better.
Excellent. Thanks a lot for that. And maybe slightly linked to that question, another one here. So looking at the models once again. So how do you know that your recommendations and or predictions are correct?
I think I mentioned the VOS system. So this was the Brains app VOS. So the idea here is that from a model point of view, if we can predict and we can simulate with those predictions, if we're in constant process of checking what we said was going to happen versus what actually happened, what we then look for is effectively data badness or model badness. And this is happening in real time all the time. So at the back of the system, those models are being tested all the time saying, you said this, excuse me, but this is what happened. What we look to see is if that drifts, then there's a remodel recalibration that's required, or there's additional information that needs to be included in them. And what we would do is, if that drifting occurred large enough, we would just redo the model straight away. But as a bare minimum, we actually like to rerun the model calibration every 3 months anyway, because that new historical data set that you've just created of that current 3-month window helps to improve the quality of the models regardless.
Excellent. A couple of questions here from Mark, so I'll start off with this one. Do you have any case histories with CCD circuits?
So we have applied our technology at the start of a CCD and at the end of a CCD, given that there's anything from 2 to any large number. At the way we've approached it thus far is to take each individual thickener as its own entity and build up, let's make each one of those perform as best we can. The ultimate aim for our technology is actually to combine the CCD material flow through each of the individual applications. So you end up turning it into its own application. So that's on our roadmap. So at the moment, the current application works well with each individual one, but there's a level of detail or a level of optimization that we think we can get by combining that feed in, feed out information from one into another.
Excellent. And a follow-up question from Mike. So he says, say for grinding, how do you get volume information / number of balls to verify your model?
So clearly we know what balls were put in and we need to have that information. So that might be a manual charge thing that the operator basically puts into our app that, you know, we've added X number of balls. We also are looking at what's coming out. So with the current model as it is, it's taking hardness, it's taking trajectory, flow, load, all those things through it, and it's making a prediction about what the ball wear rate will be. And then that's being tested by looking at what actually balls are coming out onto the ground at the end of the process. So it's a constant feedback loop. And if that model then starts to drift, we take that information and reapply it to relearn that your conditions, maybe hardness, maybe some other things were subtly different, and we can then relearn the model.
Excellent. So there's basically, I guess, a trend here of rapid relearning
Yes.
of the model. And yes.
Well, the trick here is to try and take that currently, in a lot of ways, there's a lot of data that a mine has that's about information that's sitting in testing or visual or these other spaces that is really good information that can actually recalibrate what's actually happening inside. The trick, of course, is time stamping that. So being able to capture that data of when it actually occurred, because that pile of balls or that mass of whatever it is needs to reflect a time period. so that when we then push it back over through the model, we know that through time X, this is the result of it. So that's part of the journey we go through with the client to make sure that information is clear.
Fantastic. A bit of a different question here. So Julie asks, is BASF's digital offering linked to your chemicals offering?
So a little bit like our, so back up. So the concept here is we're trying to build this around first principles, yeah? So a thickener works the way a thickener works. And what we want to be is agnostic to the equipment, to the ore type, and to the brand of the chemistry. So that's our intention. So generally speaking, what we look to do is whatever chemistry you have on the plant, our system is trying to optimize that result. Having said that, given that we know our chemistry and we know how our chemistry interacts, we feel that we can do better as a combined thing, but it's not a natural link. So there's no guarantees if you have both, it'll work better. But the intention here is that we believe that we can understand those interfaces far better with our own, but the system's designed to be as agnostic as possible.
Excellent. I'll ask the next two questions together as they're down the same track. So the questions are just straight up, how accurately can this system predict? And then the second part of that is what happens if the data is poor or there isn't enough data available?
So accuracy of prediction. So the way we approach this is the number one thing that we actually look for is not necessarily accuracy, it's robustness. Because what you don't want is a system that's giving you recommendations that continually has a lie down and says, sorry, I can't do that. It can be super accurate, but it can only be accurate one time in 10. The idea of what we try to build, and this is why there's so much research being put into the back of these and why we think coming with a preconceived first principles approach means that they're way more robust. So how accurate is the prediction? The intention is to make it better than what you've got. There's always scope for more, of course. There is certain circumstances where the system will say, well, based on the current incoming data, we can't make a prediction because the data quality has dropped. We might have lost a sensor, something might not be there. So it also has a functionality that says, don't give a prediction unless the quality of the data coming through is actually okay. That was the first part of the question. What was the second half of the question?
Just about if you don't have enough data or if the data is poor.
So a little bit like that. So when you don't have enough data, it's how long is a piece of string? I think everyone would be surprised about that. Mining has lots of data, so it's not necessarily enough. It's about the quality. We do spend a lot of time in our processes of actually looking at the quality of that information. A lot of people think they have to be perfect before they can apply this type of technology, and the answer is no, they don't. It's about making what you've currently got better. So in some cases where there's clearly something missing, there's ways then of looking at that and saying, well, is there a virtual sensor that we could create that replicates that system? Now, it might not be as accurate as the real sensor, but still better than basically zero. And the idea being here is that we can then apply that type of thinking. You still produce a model. The model still has an accuracy. It's probably got a higher degree of uncertainty. So if you had the instrumentation, that uncertainty would be less, but still better than zero. And that's the intention. This is this robustness component that we try and talk about.
Fantastic. A question here from Asif, and we also have a follow-up question after it. So this is very interesting to know the modeling for maximum productivity. Is there any modeling for asset management, specifically for corrosion in regard to chemistry?
So no, not at this stage. What we've targeted ourselves from a partnership is to look at giving optimization around those processes that we think have the high value for you as the client. But topics like what you've just said there, so corrosion, scale, there's a whole heap of things that inherently within inside that material model and the underlying platform, there's data and information in there. Now, is there a model that we've built around that? No. But is there things that we can start to explore that once we're on site and start to see what cause and effect relationships are in there? Absolutely. Can we work with individual sites and actually build a model around that particular topic? That's something that we're always interested in doing. So we're at the very beginning of this journey, Sheldon, as you can appreciate. And it's great ideas like that we want to keep adding to the roadmap. And again, that's what comes back to the concept of our SaaS model about being a partner to direct ourselves in the direction the client needs us to go.
No, fantastic. And based on what you've said so far, it does sound like continuous improvement is a big part of what you're offering and as that ongoing service as well. There's just a follow-up question to that as well, and it's how is this different to advanced process control?
So APC, I think the number one thing I think that you could highlight the difference between the two systems is it's about the prediction component. So an APC, yes, it's about doing some really clever things. It's about making sure that the set point that you've targeted you can control to, absolutely. And APC are doing some incredible things around that. But remember, what we're trying to do is give you recommendations about the set point, about what is the target you should be. It's also about future looking things. So APC, as far as we can see, doesn't do the future real well because those models aren't built around that. Whereas what we're trying to do here is to say, if we think about what's happening in the future, so grinding as an example, we might be looking from a mill overload point of view, 10, 15 minutes into the future, whereas thickener, it's an hour into the future. So if we're giving recommendations about how to anticipate what's happening, we can sit on top of an advanced process control system and say, well, this is the set point you need to track to. And we're considering upstream, downstream, and predictive components now allow the actual advanced process control to control to that set point. That's a really interesting combination of excellence on top of excellence.
Yes, fantastic. Question from Ben. So are virtual wear sensors in your grinding app built on historical actual wear data and are liner profiles incorporated into predictive wear?
Absolutely. So the models, the particular model around liner wear and ball charge is very complicated. But inherently what it comes down to is we take all the conditions that we know from a modeling point of view that create wear. We then calibrate that to the actual wear. So from a historical point of view, we need to have some idea. So we start with first principles approach. We start putting that in. Then as your liners then begin to wear, the trick is that when you go in for that liner wear replacement, we do the measurements. We actually feed that information again back into the model and say, well, our prediction is it should be in this, but it wasn't this. So recalibrate the model. And as that gets better, then the accuracy goes up. But the trick here is not just about looking at, well, what was the fact that the model was out. It was about connecting it to what upstream parameter that we were using, be it hardness or load or velocity, whatever, ball charge. There's many different factors. Which one of those and at what weighting did they impact that model? So it's about trying to understand that in a little bit of a dynamic approach. And so it's continuous, particularly when your ore body changes. I think we've said things like this, maybe not in this call, but the known known's easy. Yep, that's easy. The known unknown, that's not so easy, but it can be done. It's the unknown unknown that you've got to be super careful about. And so it's about that recalibration is about picking that up and actually continuing to look what's going on. The last thing we want to do is create a model, base it on your data, like do a data mining exercise, and the model only works for this very narrow constraint. Come back to first principles. What the intention here is that it's robust and it should work over a lot of different parameters. And that way, then we continue to always drive towards excellence and recalibrate it to ensure that that is reaching the highest degree of opportunity as we can do it.
Excellent. Still more questions coming through, which is great. And yeah, you're certainly doing well to get through a lot of these, Ken, so that's appreciated. Another question here about costs and ongoing support.
Mm-hmm.
But as part of that, they ask, and I'm happy to help you follow up to provide information afterwards. But as part of that, they ask, can it be rolled out circuit by circuit, i.e. if budget allows, roll out thickeners year 1, grinding year 2, etc.?
That's actually our preference. This whole concept of pit to port is terrifying as far as we're concerned because there's so many relationships and subtlety in the process. So what we would always look to do is pick the place where you have the most need combined with the most value that we could create. You begin there, you get value in that, you do the change management component of that because that's a big part about this. You can parachute a solution in, that's easy. Making sure the solution is used and generates value, that's the trick. And that's very much about time, it's about change management, it's about really working your way through. And once you've got something working, you can use that as then the point test to say, there it's working, let's now apply it somewhere else. And again, you might find there's certain places where there's no value in it. So why do a full pit to port? You need to be super careful about this and apply the technology where it delivers value.
Excellent. Question from Carsten here. So could your system or model be used to provide feedback to geologists so that they know what to look out for when they map out the resource? For example, he's put their mineral chemistry grain size.
It's a really interesting question, actually. So we have another application which we haven't spoken a lot about today that IntelliSense are more involved in, which is our stockpile application. So there is a logic that says if I've taken my block diagram, I've tracked my movements of that into my stockpile, I now know then what went into my plant. At some point, I now have recoveries. I have impact upon a whole heap of parameters. Now, if I've tracked a whole heap of things like hardness, all those items that were listed, and I've tracked them through, I can start creating models and relationships about, given that this is what happened, or this is what was there, this is how the plant behaved. We can start then to actually give advice to the geologist to say, well, in your block model, avoid those blocks. They aren't going to work real well, or these are the ones that are better. I think the better way of doing that is to try and find this combination of saying, well, you can't just avoid part of the ore body. It's about how you then do your blending, that you produce a stockpile then that is chasing that right combination of throughput and value. And yes, so the answer is yes. It's an interesting journey of how that would actually work through. But that's something that we clearly want to be able to drive that cause and effect piece, connecting these things together. So you no longer have this silo approach. How often do we see the plant blame the mine and the mine blame the plant? We need to work out ways of having this material flow, allowing this thing to roll through, and then its impact to be fed back into a real-time closed loop approach.
Excellent. That's a really important point as well about increasing transparency across that upstream and downstream as well. So that's an important point. We'll just get to a last couple of questions now. So is virtual sensor supported by simulation model or predictive model?
So the virtual sensors themselves produce predictive models. So the concept is to create a virtual sensor, you have to be able to do some predictions around it. So you build those prediction models, you test the value of that virtual sensor using the simulation. So now that I've got a virtual sensor, it produces something that's real. So that might be predicting something in real time, i.e. what my balls are doing. I can't see that in real time. Yeah, the simulation then is about testing, well, what did you say versus what happened? So in the case of your mill balls, when they start pouring out in the ground, does that reflect what the model said? So you build them around prediction and then you test them using the simulation.
Fantastic. This one might be one that we can follow up on with afterwards, but Jag has asked if you can share some experiences with dozers and excavators.
I think we'll follow up on that one because it's a it's a small question, large answer.
Fantastic.
Potentially.
And of course, if anyone does want any more information, we can put you in touch afterwards, so that's no problem. We'll finish off with this question, and that takes us to all the time that we do have. So can sites use brains.app with their own data platforms? So
in this case, so what this question is about is a lot of sites are building their own data lakes. Yeah, and their own platform where they're hosting all this information. They might have done a lot of that pre-work in terms of the quality control. So the answer is, of course it can. It's just another data source. So we would still bring it into our system, but if half that work is done, that's great. It just means that there's less work required. But yeah, in some ways, absolutely, because there's insights that the client has about his own data that we might not necessarily have. We would still do more with it because that's the whole point of what we're trying to do. But cutting that corner, yeah, it's a nice way to get it done.
Excellent. Well, I think that's a good point to finish on. And you've, as I've mentioned there, you've done extremely well to get through a lot of interest and a lot of questions there. And I think it really goes to show that what you're doing there at BASF, it's really something new and innovative in the industry and can really change the game for operations. So thanks a lot for presenting that today.
Absolutely. I think there's been a lot happening in the mining space. We need to now start to embrace what's possible in the plant space, which is where we're really trying to focus our attention.
Fantastic. Thanks to everyone who's attended as well. You will receive a copy of the recording of the webinar as well as the slides this afternoon. So you can watch that back again at your own time. And as mentioned, if you have any more questions for Ken or the team at BASF, we're more than happy to put you in touch with them. So once again, thanks everyone for joining. Thanks to you, Ken. That was an excellent presentation.
Thank you.
And we'll see you all next time. Stay safe.